part to know entanglement, because this is where J. proved that it was entangled, and in sort of way we can say proved Einstein wrong, which is always the thumbnail catchphrase. So before starting off, I'd like to say I'm not a very, I haven't read all the things, so there may be some mistakes here and there. So I'm ready to get rectified any point of time, and we can all together laugh at the mistakes, I guess. That's better to get them started. So let us first understand what the problem was, and why was Einstein, Podolsky, and Rosen so triggered with this one topic. So it was like they assume that there are two particles, or we can say photon, electron, or positron, and let us say in some way they interacted with each other in the past, and because of that now, at the time they were not expecting it to be entangled, but then they were in somehow correlated to each other in a sense. So what Einstein thought was correlated when correlated. Once they are interacting, they're correlated.
But in the past or currently?
Oh, that's a good question. I never thought of it. So I guess in the past, if they are interacted, then they must be correlated. So
we expect it.
Yeah, we expect them to be correlated now. So what they assumed was these two particles not to be visible but very far apart. And Alice and Bob are here and there standing. So I mean, not here, but then they are bombarded from here. Like there is one nuclei that produce two particles, an electron and a positron, and both of them are now going off in this direction. And now there are A and B people standing here and there. And now what Chalaki did was we can measure anything in any direction, and we have so many operators. So what they did was they decided to measure, let us say, X and P. So A decided to measure the position, while B decided to measure the momentum. And as initially the system was at rest, so if this is the position, so equally spaced from there, I mean, if we know position and if we know momentum, and as we know that the total P of system is conserved, so from this we can finally find out each and everything about both the particles respectively, which violates Heisenberg's uncertainty principle, of course. And at this point, in the paper, I'll actually read from it. वो पढ़ने में अच्छा लगा.
So why they have to consider Heisenberg as correct? Why they seriously do it?
Oh, exactly. So I don't have a good answer to this, but then
what is so certain about the uncertainty?
I'll have to think on this, I guess. I mean, sir, do you have an answer? I think that it's because the thing that we discussed, that to predict that if an electron is within the nucleus, we can use Heisenberg's.
I mean, by 1930 or 1932, Heisenberg uncertainty was explained and demonstrated also, experimented. So you cannot say that it is
right.
Wrong.
We can't.
I mean, this paper was written in 1935.
Yeah. So they claim that if two physical quantities, let us say A and B, do not commute, I mean that is AB is not equals to BA, at this point of time, then precise knowledge of one of them precludes the knowledge of other. I mean, if we know one thing, then we can know other. Furthermore, any attempts to determine the latter experimentally will alter the state of the system in such a way as to destroy the knowledge of the first. So, इससे उन्होंने फिर they propose two things. Either one of the two is right. One, the quantum mechanical description of reality given by the wave function is not complete. And the second, when the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous realities. Okay, big words. So we'll try to understand this in a simple way. So what they said was these two particles, if the information is to be transferred or if the other has to be knowing what this particle is measured or not. So the information has to travel greater than speed of light in order to be instantaneous. And because Einstein being proved relativity and all these things, and because of this thing, so he was a bit, on the backside of this, and this is what they call local realism. While the second thing, which was daunting them, was the deterministic nature. I mean, the probabilistic nature of this thing, because what we now know is that these are in a state, in a superposition state of up and down, let us say. But as we measure them, then they get collapsed. But as Einstein was not ready to accept these things, so he decided to assign hidden variables to this thing. So he claimed instead of these particles to be in a superposition state, before leaving only, they have decided to be in what state they are. That is what the hidden variable is in crux.
Leaving where? Before leaving from where?
Before leaving from here. Yes. I mean, and then A is just measuring to measure. While in quantum mechanics, it's like before measuring, we have the state in superposition. And after measurement, the state collapses. But Einstein claimed that the state never collapsed. It has already, been determined here. So this was the second assumption. I mean, a point to be daunted on, not assumption. So on this two bases, they wrote this paper and questioned quantum mechanics. And then Bell came in and gave his infamous Bell's inequality to, in a way, in a statistical way, prove that what Einstein was thinking, that a local realism exists. This was proved wrong because of that, and the deterministic nature was also then proved wrong. So, I guess is things clear. So we can get more right? So now let us assume.
So in short, what he is telling is that before doing measurement, you cannot know anything.
Yeah.
Okay. But Mr. Einstein has assumed that they know everything before the measurement. Okay. So that's what he's trying to say. Deterministic knowledge.
Yes. And then another famous quote from Einstein says that he says that a moon is there even if I'm not looking at it. That is the point of him saying the deterministic nature of nature and deterministic nature of nature.
Actually, I have a question.
Yes, sir.
You said that Bell proved that these assumptions, local realism, and deterministic, both are wrong. Why it is not only one is wrong and one is because anyone can falsify and prove the mistake.
That is going to tell you.
I guess I'll tell you. Let's
See, that the thing he told that it's a moon there, even if I am not looking at it. That is a deep question, which is still unresolved. Okay? Clear?
Let's see.
So actually, this resolution was given by one of the top computer scientists.
Yeah.
Okay, computer engineer, who got interested into quantum mechanics. Okay.
Whose name is Bell, as we usually do. So to understand this, we'll go through let's first understand in a simple sense what this inequality is and it holds true or not. So as it is written, let us have three sets. One set says that number of people wearing hats, another scarf, and another one close. So, in a very crude and simple sense, what this, and let us call them A, B, and C to be simple in writing inequality. So, what this inequality says that A not B plus B not C will always be greater than equal to A not C.
One small comment from my side. This not is not get and not.
Yeah, I mean,
This
I'm
is
writing in
English.
English. Yeah. So let us just give some random numbers so that we can come to things. 5, 6, 7. So in chorus, if we can say A not B, so people wearing hats but not scarves. So how many number of people are there? 1 plus 2. Right? Thank you. And people wearing scarves but not gloves. How many number of people are there? This is 2 plus 3. So this is greater than equal to the number of people wearing hats but not gloves. Right? So that is 1 plus 2. Which we can see is of course true in a very in the number. Yeah. And even if we take any one of this on this side and put it on the other, then too it holds true. That is the another magical thing about Wells inequality.
I mean, there is nothing quantum in this.
Yeah, this is
This is
just
pure logical.
yeah logical thing, which he proved in his paper, and that is a tedious paper to go through. So I haven't went through it completely. So now that we this thing was Wells inequality. Okay, this simple expression of A naught B plus B naught C is greater than A naught C equal to. So with this inequality into our picture, so now what did Well do? He did what we learned in our school grades 8th or 9th. How can we prove something to be right? By proving the opposite wrong by the method of contradiction. That is the basic thing which he wasn't expecting. I mean, he was just solving, and at the end, it contradicted the initial assumptions. That's how then these two claims were falsified. So let us take a system that is generating a pair of photons on both sides now. Let's try to give it computation. So this is generating pairs, and there are two observers again, A and B, on both the sides. And now, as these are the pairs, so this both
So
will
is
be
there any experimentally available source? Have you come across it?
not like this, but then Bohm actually did a paper.
That is, experimentally you have to find the photons, no? In that entangled pair, right? So what is that? Any idea about that?
Entangled photon. I mean, we can see double slit also, I guess. Coherent. No?
So have you read about this calcium cascade process?
No, sir.
So the exact calcium atom you can get that by getting dehydrated, it will produce an entangled well state.
So now A and B, they both are standing on the opposite ends, and these both are coherent pairs of photons, and they have polarizers with them. We haven't decided what angle these polarizers will be, but then these are polarizers. And we have 3 polarizers with us. I mean, each one of them has individually 3 polarizers. One at 0 degree, one at 45, and one at 90 degree.
So A and B are having three polarizers.
Yeah, individually they are having 3 polarizers, and randomly they will be selecting any one of the polarizers, and then they'll be seeing the measurement. So, how this experiment goes is, as far as I've explained it, and they will be selecting random polarizers, and this pair of photons will be of different polarization. I mean, they will be unpolarized. Let us say they are polarized, but in different directions at every point of time. So at that we have a random sample set. Yes.
So from this source with the photons are coming, what will be the polarization? Is it left circular, right circular, or linear, or what is it?
Oh, it's a good question. I never pondered on this.
No, because you are going to use the polarizers, right?
Right.
You have to know which type of polarization is there.
Exactly.
Otherwise, as I told you, we have to apply the half wave plate or a quarter wave plate to change the polarization.
Right. Let us assume them to be linear polarization. Yeah, that will be easier. And these also just classical, for example, we are not going on. So let this be polarizer 1, 2, and 3. So what can happen is either a photon will be now writing a combination if whether a photon will pass through polarizer 1 or not.
I mean, what I'm trying to say is that it is either horizontal or vertical.
Right here.
That will help you in discussing this because you are having cross polarizers. Right?
Yeah, right. Okay, so now that we have only 2 possible states and 3 polarizers, we have 2 power 3, that is 8 possibilities of what can exactly happen right now. So it will be either that the photon will pass through 1, 2, 3, it will pass through 2 but not 3, it will pass through 1 but will just pass through 3, then it will pass through 1, not both, then this, and this steady ground is and none. So 3, 6, 8. We have this 8 possibilities. And now we can have either A having 1, B having 2, A having 2, B having 3, A having 1, B having 2. So this are the possibilities that these will connect, and if A is having 1, A is having the first polarizer.
Why you have it 45? What is equal to 45 degrees?
Okay. Yeah, I actually missed that part.
That point is the most important.
Yeah. So if we have an unpolarized light, and if we pass it through a slit, a polarizer, then the intensity reduces, as we know, by the law that we have, of Moore's law. But then, let us say we are passing it through the vertical polarizer, that is theta 0, and then we are passing it through 90-degree polarizer, then no light will come on the other side. Why? If we just put in one polarizer of angle 45 degree or any other angle in between, so there will be some intensity of light that will come out. So you have to know light. So here we are still somewhere.
In between, if I put that suddenly, you will suddenly get light. That is the intensity.
Yeah. I mean, as far as I understood and interpreted from what this means is, our measurement also changes the stage, like the measurement that we do. That's why this is trying to be analogous with what we are trying to do in quantum, but not completely. So, thank you, sir, for reminding me. So now we have now we just have to work out this simple probability. So we will be writing only 2 notations, same and different. Same means if the photon is passing through 1 and photon is passing through 2, let us say we are talking about this, then it is passing through both, so it will be same. If it is not passing through both, still it will be same. I mean the outcome will be same. So this is also same. So this is same, this is different, this is different, this is different, this is different, this is same, this is different, this is same, this is different, this is different, this is same, this is different, this is different, this is different. same.
D property.
Yeah. I have a very bad impression. Sorry. So now you may be asking, we have forgotten three more states here, which could be like 1, 1, 2, 2, and 3, 3. But then those are the very obvious ones where we know that those photons are bound to pass through it. Right? So that those are not of our relevance, and here also they are passing in any condition. So what this is, I mean, let us say these are the hidden variable parameters, and if let us say the photon 1, let us say photon 1 1 and photon 2 1, these are coming out, and in one of those, if this hidden parameter variable is acting on it, and if
So the superscript is the hidden variable parameter.
yeah, superscript, and these are 1 and 2, A and B. You can write it as A and B. More understanding. So for this, then if they take any combination, any one of this, then they will have the same result. That is what is to be understood from this. While if they have, let us say this fifth, we are having let us say 5, any number, and if this hidden variable is acting on it, then if they take 1 and 2, if A takes 1 and B takes 2, then they won't have the same result in this case. While if they take 2 and 3 respectively, then they will have same result. So this is what is to be understood out of it. And if you see over here, the probability of getting the same outcome is 1 over 3. Okay. Simple math. And when we did the experiment, I mean, I referred it from a video actually, so I'm also a bit curious about how this number came. But when the experiment was, run, simulated, then they got the probability of it coming out to be 0.25. But then we got the outcome to be 1/4, and as it should be greater than this. That's what the Bell's inequality stated, which is false. That means the states are entangled. This is because this is false, and so as I said, we wanted to.
1/4, how did it come from suddenly?
Pardon, sir?
Suddenly 1/4 came from where?
हाँ वही मुझे भी नहीं पता वो. It was mentioned there, and yeah, I took it on God's grace. So it came as 0.25. I guess they must have simulated it, and then it must have come as this. So the basic crux is this inequality doesn't hold true, and the other options they took was this, and on basis they started this. So this goes wrong because this goes wrong, and hence the quantum theory is valid. Victory.
With probabilistic quantum theory.
Yeah. Yes.
As suggested by Schrodinger.
Sure.
Till today, I mean,
Might be the next one.
it may be proved wrong, not wrong, because there are so many ample evidences for that. It may be proved that hidden variable will exist.
Yeah. But then till date there are no such hidden variables.
That's why it is hidden.
Yeah.
Once it is not, cannot be called as hidden variable. Finished?
And one more point I'd like to add. This was just a simplified version of the Bell's inequality. If we want to know the real part of what inequality is, so I actually noted it down from a chapter written by Ramkarthik sir only. So these are the two relations versus theta, where theta is a hidden parameter, let us say, and I mean a parameter of measurement. As I said that we were measuring this in the polarization only, the same treatment is given by Bell and also sir in the textbook. So let us, and I'll directly write the findings of what is there. So the classical part predicts this to be a straight line. This is and just taken as an equation minus 1 plus 2 theta by pi. This is very well proved in Sir's textbook. I'm trying to grasp it till now. As soon as I am, I'll also do that. And what the yeah, I'll tell you. And what the quantum counterpart suggested is an equation like this, which is cosine equation. So as you can see, it matches at some points. By
minus
theta 0 पे minus पर. So as you can see, in some parts it is aligning together. The theories are aligning. I mean, equality is holding. While in some parts there is some deviation, which we can observe. And yeah, so another thing is the bound is 2 in such a case, and if a state is able to break that bound, then that state is entangled. And the inequality that well proposed in this paper is as follows, where S is equal to mod E AB, this is the form minus E of A B dash plus E of B dash plus E of B dash. And this has a maximum bound of 2 or 2 root 2 in something. But 2 root 2 only. This is a good one. And this is the Bell inequality, where they take two angles A and B on, let us say this is observer A and this is observer B. So A has two outcomes possible, that is A and A dash, a small a and small a dash, and while there is B and B dash. And then this is the result that we proved on to be there. And the thing that I pointed out, that the negative sign can be anywhere, is a very fascinating thing. So this is the Bell's inequality that I'm still trying to understand. Let's hope you all understand it one day. Thank you. Any questions from?
That was